think this TK as timestamp, and session control signals, CK, at the input features. So the input features was originally A and V, and T and C is also concatenated. And that's all. That's it. But the to improve the model performance and computational efficiency, it actually tries to compact the recurrent neural network into like compact, little smaller size. I'm not so sure about how do they reset these GRUs, because they were very not clear about. But I think it just means resetting the GRUs. But anyway, they claims that it improves the model performance, or at least to show the comparable performance, and also improves computational efficiency in both memories and the throughput of this model. And they claim that it improves architectural compatibility, which means that instead of using GRUs, they can use LSTMs or other transformers or something like that, some other model RNN models as a base of this HRNN meta, base model of this HRNN meta. They use this control signal to efficiently run this algorithm, but each HGRU, this means that the user level, this refers the user level HRNNs, and this GRU refers session level RNNs that was mentioned earlier, and they think that it can be replaced with other models, but they didn't mention the result. The feedback encoding, it's simple. They use some extra info, basically like contextual info, as a metadata. They can they also like basically concatenate this user feedback info into info features. It includes like user features such as ages, dynamic features such as device, or feedback events such as purchase or costs of that item. They say it improves model response to implicit negatives. By negatives, I mean since as a by I mean the no click. What I'm saying is that when I'm saying positives, it means user clicked on item, and by negatives, I mean the user did not. And the implicit negatives means that unintentional negatives, such as like refreshing without any clicks, or just short dwell, random visit on web pages. They say this metadata can like improve the response to these implicit negatives. Item feature decodings. The item feature decoding is, of course, in the decoding phase, and it has it actually computes two set of scores. One that is done by standard standard way, but the other is done by like peculiar way. I'm not sure about how to interpret these equations, but I'm guessing this might be working as an identity like function, decoder as an identity function, like to like explicitly supervise that when this score is high, this score has to be low, and when this score is high, vice versa. So what the lambda, the hyperparameter, actually, the random value lambda is working as like a dropout that in training time to randomly choose between these scores, and when this score is high, this score has to be low. So I think they build this the mirror function of this standard decoder, using just weights and biases for hidden representation in RNN. But I think the FJ in here is basically the same as the HK, and they are probably something like going when they are multiplied, it'll always be like 1. I'm not so sure about this, but I think it is something like explicit supervision for supervision, yeah. And they say it is very useful for cold start scenarios. The FFM is short name for field-aware factorization machines. This, I think, is a method of the data preprocessing for recommendation system. Standard way is factorization machines. When given a raw input data for recommender system, every field has one latent features, such as this feature and value. But in FFM, it is not. It for every per every field, several latent features might be existing. For example, given a field of publisher, it could be actually this might be easier. For a given field of gender, the feature is male, but it can be also female. And in FFM, they formulate this gender that represent the field, and the G female that interconnects these fields and feature name and its value. I'm a little confusing about this FFM, but I looked for the some examples of this FFM and found this link that it basically builds the indices for indices for fields and each interconnected features, and it uses tuples to represent a feature, and it improves the contextualization of the raw input features. They claim is what they say. The importance actually we already walked through the key components of HRN and meta, and another additional solution this work presents is importance sampling. It keeps the computational complexity efficient during training by approximating the loss only on the sampled subset of data, the entire data. How they do it is that they formulate the loss as a policy optimization problem that aims to maximize rewards. By rewards, I mean the positive clicks. So if you write the loss it's actually the log softmax. This is softmax and log cross entropy loss between. This represent the scores. So the scores of given by the, output by the decoder, and its true labels, which in this case is rewards. And by leveraging negative sampling to approximate loss, we can formulate like different, more efficient way of getting approximating the loss between positive sample and negative samples. The loss can be written as this. This represents the scores for the positive samples in a random pair of positive samples, and this represents the scores for negative samples in random pair of the sample data set. And that loss can be also revised as into this form, given that assuming that the distribution Q is already known QJ is should represent the frequency of an item AJ. AJ. User access the frequency or user access the item AJ. So you can get the scores, and we can easily compute this frequency, and we can just use this loss to compute to approximate the loss. When you're using, we have to calculate this loss for the entire data set, but we don't have to do it in this form. So it's very computationally efficient. Item trend corrections is also known as ITC. It divides the fast-changing item trends. So it divides trends. By trends, I mean the popularity or the exposure rate or the frequency of an item appears to users. It is different from the click-through rate because the click-through rate represents the probability of an item is clicked, given that the item is already exposed to the user. And in recommendation system, they don't trust this item exposure rate because it varies from time to time, so it is not reliable data. They want to remove this bias, so they want to figure out these values, the exposure rate. It is the unknown term in these equations that has to be solved out. It is obtained by item trend decomposition that separates out the click rate, the left term here, and the exposure rate, the right term here in this equation. We can obtain this value, the approximated value, from the scores, and we can obtain this click rate because it doesn't really change, I think. In the papers, they say it can be obtained from global click-through rate in the last training. So we can obtain these two terms, and we can obtain this term, and we add this the bias term to the score, and to remove the item exposure bias for specific item. So and after that, they somehow retrain this model, but it is not clearly stated. I will introduce the experiments. There are